Good morning, everyone. My name is Arsalan Khan. I am the Director of Technical Marketing at Graphiant. Unlike Ali, this is my first time here at Networking Field Day, so I'm very excited to be here. So what we're going to do is let's start and dive into the solution itself. This is the same visual that Ali shared, giving you an overview of the different components of our solution. So it gives you a high-level idea of what the overall architecture looks like. Now, the key areas that we're going to go through here are, we'll talk about the Graphiant Cloud, talk about how it enables us to do zero trust bringup. We're going to talk about the stateless core, go into the details of what makes the stateless core, how it distinguishes itself from other solutions, talking about tunnel scale, talking about SD-WAN, MPLS. And then we're also going to talk about the gateway. So how do we provide cloud connectivity, leveraging these other components that we've built in order to try and solve a lot of the problems that people see in their networks today. So for zero trust bringup, the key features, the key areas that we've focused on is from a edge bringup point of view. You want it to be certificate based. The idea is, how do you keep this set up in a way where you don't have to work with pre-shared keys? How do you make this a secure automated bringup, relying on some of the best security technologies that are out there? Now, when we start to look at encryption for the actual data traffic itself, it's important to have end-to-end encryption. No decryption possible in the middle mile. Even if we as Graphiant wanted to try and decrypt, it is not possible for us to do so based on how the solution is designed. And then the last part becomes, how do you do pairwise encryption? You want to ensure that all of your sites, all of your edges that you have, when they are communicating with any other site, only that source and that destination are the ones who are able to decrypt the traffic. From a orchestration and bringup workflow, when an edge comes online, trying to join into the Graphiant service, as it starts to get brought up, it's going to reach out to the cloud. In the cloud, it's going to be able to authenticate itself as a valid Graphiant device. It's going to download a set of certificates that it's going to use for future communication. It's going to receive access to the control plane as well as the data plane. But before you get to that step, it shows up on the Graphiant portal where an administrator has the ability to go and say, yes, this is an edge that I recognize. I would like to allow it into my network. Once that edge is allowed into the network, now it sets up its control plane connections, sets up its data plane connections, and now it has connectivity to all other edges. All right.
In terms of your bring up, and Ali was talking a little bit about secured or DoD or government clients. Can you talk a little bit about what the vision is in terms of, rather than having your edge device reach out to the cloud, how does that process happen in the case where you've got a network that's, it's not allowed on the internet? There.
So for that, what we are exploring various private networks, how we're going to build connectivity out for it. And depending on the kind of requirements that exist, if you look at most cloud providers, they themselves started with, we're going to have one cloud that's going to service everyone. When requirements start to get more stringent, they said, okay, we'll build a gov cloud. Now they're announcing, oh, in Europe, there's different laws around how data is treated. We're going to build something that's sovereign mostly to the EU. So for those kind of scenarios where there's special requests and circumstances, that's a solution that we are capable of building, but it's not the first area that we're focusing on.
Are you planning to go through the process of getting your private cloud certified for government use?
Long-term goals, of course, that's something we're looking into, but those tend to be very long processes. So if we talk again in 10 years, maybe I'll have a better answer for you.
And just to follow up on that, so does that also imply that there would be a separate stateless core that would be built for highly sensitive, secure government type environments?
So for the stateless core itself, because there is end-to-end encryption, there's nothing that can be done in that environment, even from our perspective. From that point of view, it does satisfy most requirements, and we are looking at government certifications such as FIPS in the long run for making sure that it works for their requirements.
Let's continue on with onboarding of an edge device. Is it typical that customers will be built out? Ali showed the different locations. Is it typical that customers will be built out with the Graphiant Core in multiple locations? And if so, how does the edge decide which entry point is the best? Is it a DNS query, or how does that work?
So it's region-based. When an edge comes up, it identifies its own location where it's placed. Based on that, we know what's the closest Graphiant location that we have based on the region that it's in, and then it connects into that region.
Okay.
There's obviously failover scenarios where for some reason the region is down, it will fail over to the other regions, but it's able to identify a primary region for itself.
Follow up on that. How does it do that? Does it use GeoIP for that
Yes,
self-identification?
Yes, we're primarily using GeoIP, but we do rely on multiple sources of information because it's not always 100% accurate.
Right. Oh, well, yes, that was why I was asking. Right.
Yes.
So second question, how does it identify itself? So you have this device, you turn it on, you say, oh, it just, it knows what to talk to, right? How does whatever it's talking to know to trust it?
Yeah. So one of the requirements that Ali mentioned for the hardware is the TPM chip. That's part of it. So for that, any device that needs to be a part of the network, that information gets uploaded into the portal. So it knows this is a device that should be allowed to connect into the solution.
Okay, so there's some sort of cryptographic mechanism that it uses to identify itself.
Yes.
Okay, that's what I wanted to hear. Thank you.
And one last question, and I promise it'll be real quick. Are we going to actually see the back end, the administration panel as part of the demo? Is that part of it?
Yes, we'll go through some of it for the demo. From an encryption point of view, so the two things that we talked about was having end-to-end encryption and then having pairwise encryption. From an end-to-end point of view, every edge that comes up into the network is going to connect to the portal. There is a key exchange that happens between these edges. So we're going to use Diffie-Hellman to do the key exchange. Both the edges then generate keys for that particular session. When traffic is encrypted from one of the edges, that traffic goes over the stateless core and then is only decrypted at the destination. And like I mentioned, with pairwise keys, the destination is the only one who can decrypt that traffic. If the packet was to be captured or try to be accessed elsewhere, not even any of the other edges in the same enterprise will be able to decrypt that kind of traffic.
Just one thing on key management. This is hard, like really, really hard.
Yeah.
Like it sounds good, and you set up your CA and you've got your client certs and everything's all behaving itself and it's all cool. And then like your CA cert expires, let's say, happened to a really large company, which we don't need to name them now, but but when I saw that happen to them, I'm like, yeah, I've been there. It's just my mistakes weren't quite so public, but that's hard. I hope you've thought about some of that as well, because it's easy to set these things up and you go, oh, setting the CA expiry date of 2032 or whatever it is, it's great, it's fine, not going to be my problem. And that comes around a lot quite soon.
Oh, it does.
You thought about that?
So I was one of the first 10 engineers at Viptela. Fairly, I know the problem you're describing.
Sorry, like space, yes.
Yes. So
It's good. It's good.
Back to this view. So if you notice the second flow where you see GEK and GAK certs, the difference in this flow is when the device comes up with a certain certificate, that it uses it in order to authenticate itself for the first time, then it receives a set of certificates from the portal. These certificates get automatically refreshed on a periodic basis. So from a user point of view, you don't have to do anything, but the certificates keep getting refreshed. So,
It's one of those things, a certificate lifetimes of what the browser's trust and everything's been shortening over. And it's actually good because it's forced us to get the processes in place to do it. When we could set it out 5+ years in future, we'd just forget about, what are we going to do when we actually need to roll it? So that's good. You've got the rotation thing sorted. That's good.
What's the period?
So there's two certificates mentioned here. There's a GEK and a GAK. This is very similar to what we were talking about for browser point of view. There is a long-lived certificate that's there for a couple of years, and there's a short-lived one, which is just there for a few weeks. That one refreshes every few weeks. So that's the one for access. And then there's a longer term for identification, and that refreshes every few years.
Thank you.
In the next slide, I had a question. So the connection that you have to the portal, is that a persistent connection and more like a control plane connection? Or
It's a persistent connection, so it handles both management and control
so
plane.
it's management plane, but not a control.
It does both management and control.
All right.
A quick question about the encryption there, and I think your previous slide answers my question, but I'm just going to ask about it anyway.
Mhm.
You're talking about pairwise encryption, so each pair that has to talk to each other, it negotiates its set of keys for that transaction. You're not talking about a group encryption key
No.
or anything like that, correct?
No, no group encryption. It is exchanged between that pair itself,
Okay.
just two. If you'll see, this is the overall network that we've built so far. So we have our host on the left, we have an application on the right, we have edges. These edges have already set up connectivity using the Graphiant portal, and now they can send data traffic over the Graphiant Stateless Core. There was a question before about IPv4, IPv6. Within the Graphiant core itself, we are only using IPv6. From a end user point of view, you can use both IPv4 and v6. So we are doing that. All right, let's talk about the stateless core. I hope we will get into the details and answer all the questions that you guys have, but keep in mind I have 37 minutes and a demo to go. Now there's three main attributes of the stateless core that we'll talk through. The first one is any-to-any connectivity. So this ties very closely to the tunnel scale problems that exist. It's important for us to be able to connect any different location to any other location in the enterprise network. Now, whether it's for a P2P application or if it's for something such as edge compute, where now you have so many distributed locations of compute that different hosts may need to be able to connect to. Then we'll also talk about scalability. How do we ensure that we can separate state of the customer environment from the state in our core to allow us to be able to scale and not be pinned down with the same kind of problems that PE routers and MPLS run into. And then we'll also talk about multi-tenancy. So the core itself is not a unique core per customer. Instead, it's a single core, multi-tenant. How does it handle multiple different enterprises? So for any-to-any connectivity, the idea here is any new location that you bring online into your network, you shouldn't have to worry about the underlying topology to try and figure out whether two locations can talk to each other. When you are bringing up a new cloud region or a data center or an edge compute location, and then you bring up other branches, you shouldn't have to worry about, am I building the right tunnels? Am I setting up the right connectivity? When you have a small network, yes, you can build a full mesh of IPsec tunnels. What happens when you have 10,000 locations? When you start thinking of IoT requirements as well as edge compute, now we're talking about hundreds of thousands, eventually millions of different endpoints that need to connect into this network. It's important for you not to have to worry about, of all these millions, what subset is going to talk to which other subset so I can build the right tunnels. The stateless core is meant to solve that problem. Now, we've talked a bit about where does the IPsec run? Do we have IPsec? What's going on? From a detailed point of view, an edge builds an IPsec tunnel to the stateless core. We'll talk about what happens in this IPsec tunnel. It's mainly for authentication and integrity protection, but it only builds IPsec tunnels to the Graphiant core. If you have 50 other edge locations, 5,000, 50,000, it doesn't matter. From that edge's point of view, it's going to set up a few redundant IPsec connections into the Graphiant Stateless Core. And anyone else who is a part of the Stateless Core can then reach and talk to the other edge.
What if I don't want any-to-any connectivity?
So that is something you can control via policy,
Okay.
but you're not we're trying to move away the control of that from being topology control to routing policy control. I don't want these two locations to talk to each other. I make sure that via policy, no traffic can flow between them. But you shouldn't have to worry about the underlying fabric itself of whether connectivity exists or not. The second important part of the core is the scalability of it. Now, if you look at the visual itself, and we start at the bottom, these are your end hosts. For the most part, in simpler locations, you just need to have a default route to your edge. When you go to the edge, that's where most of your enterprise state lives. So all the routes that you have, whatever security associations you need, all of that lives in the edge itself. And then when you look at the stateless core, none of this information is propagated to the core at all. The core only maintains its own state of what other core devices are there, what edges may be connected into this, but whether you have 5,000 routes, 500,000 routes in your network, those are not a part of the Graphiant Stateless Core. If you compare this with MPLS, the PE router is where you run into the most scale issues simply because it needs to maintain state of so many different customers. That is the part that does not exist in our system. All your state is existing on your edge. The stateless core just knows about the core, knows where edges are, does not know anything about your private network. This also works out well for us because in terms of cost, when you're talking about compute, when you're talking about memory, we have a significantly reduced footprint where you could take an x86 box, a $30,000 box, instead of having to worry about $1 million CPE, sorry, $1 million PE. You can deploy those. Those are your core routers. That in turn means we can operate this service at a much lower price point just from our own point of view. And then if we talk about data center space that we may need, we're talking about trying to go green. Not going to say that was the reason we went this way, but if it happens, so it happens.
A question about the scalability here. In order to achieve that, are you extending the SRv6 capabilities all the way out to the edge then?
For the edge, yes. So it does use labels, and we'll go do a packet walkthrough so that you know what information is where and then how the label stack works. Now, the third key point about the stateless core is the multi-tenancy of it. Now, the core itself is natively multi-tenant. What this means is as new tenants are added into the environment, it does not require any changes on the core itself. There is no configuration that we need. There is no change control window, no 50 network engineers reviewing configuration. All of this is just natively built into the core where a new enterprise shows up. The core needs no change. Now, because it is a multi-tenant core and you have various different customers on it, it's important to have segmentation within the core itself. So we are using labels to be able to track different segments that exist, but the core itself does not need to know any information about the enterprise per se. What it just cares about is this is a new segment that I have to deal with. All right, now the meaty stuff. This is a step-by-step of what a packet goes through as it flows through the Graphiant network. So we'll go into each and every step, talk about it in some detail. But as we start out, the original packet comes in from your device. Step one is where it goes from the edge into the Graphiant Stateless Core. Step two is how it's routed within the core. And then step three is how it egresses out of the core, going to the remote edge. Then the remote edge is going to decrypt the packet, and it's going to be sent to its final destination. Now we'll go through the full set of headers. There you go. One more image that's squished. All right, so let's focus at the bottom part of this visual. The traffic is starting from the host all the way on the left. It goes to an edge, and then it's going to go into the core. If we just focus on the part of what happens when the packet is in the edge leaving for the core, there is an ESP encryption header that gets added on. So the original packet gets encrypted, and then an ESP header gets added on. Then we're going to put on an IPv6 header. This is what's required for our internal network between the remote edges. Then we attach a Graphiant label. So this is the label that's going to deal with what path you're going to be taking. This is the label that deals with what segment you're a part of. This is the new metadata label that we have in our solution, where we add all of these capabilities using these labels. And then,
So, quick question.
Sure.
Quick question.
Mhm.
The IPv6 label that is so that's the SRH, right? The segment routing header that
Mhm.
you're pushing onto the packet. Within the Graphiant label,
Mhm.
is that, are you going to go into detail on what that is? Is that just a flow label that you've sort of adopted, or
So the label,
what is that?
this label tells you what core you want to send the traffic to. So what the egress core is. That way you can determine that from my own source of this is the core I go into, this is the path I needed to take, and this is where I want it to exit.
So that's all part of the SRv6 suite, then,
Yes.
correct?
Yes.
Okay. Now, just to pull on that thread a little bit more, is
Mhm.
that, I'm assuming, and you can correct me if I'm wrong, or you can ignore me altogether, that you're using the Linux implementation based on the ROSE code for, kernel support of SRv6. That's the only implementation that I know of. So what I'm really trying to suss out is, did you build this all from the ground up, or are you building on top of known existing code base?
So there's
Again, you can ignore that question if you want. I know it's fairly deep.
Yeah, we can. I can share with you the implementation that we're working off of. So it's not the Linux implementation, but there is an existing one that we've augmented. So we're primarily, the main difference is our implementation is all in Rust. So in order to be able to run it in Rust, which means there's some existing that we built on top of, but it's not the Linux version that you're thinking of.
Oh, interesting. I would like to know more about that at some point.
Oh, sure. Happy to connect with you after.
I have a question.
Yes.
So talking about the Graphiant label, and it's got destination information. So in a secure-less world, you would be able to send to whatever remote edge you wanted. Where do we get the security that says I can put, the orange label on my stuff, but Jordan's label is going to be green, or in Jordan's case, I can talk to Seattle and Tokyo, but I can't talk to New York.
Mm-hmm. So the label itself, kind of along the lines of the segment information being embedded in the label. This label that you tack on, there's certain labels that you are allowed to tack on. So that label itself includes the information.
Okay, so that would go edge by edge, right?
It varies edge by edge of what paths it's allowed to use. Yes.
Do as a network engineer, do I have the ability to say, this is going to be my baseline security across all of my edges?
Yes.
And then, and then you can tailor on top of that?
Yes.
Okay. And how does that information get pushed from, my edge in Seattle to my edge in New York? And
so that's where the controller comes in.
okay.
That distribution across edges happens via the controller.
Okay. Thank you.
I'm also going to lean into the Graphiant label just real fast. So if I were to pull up like a packet capture off of the host or capture this in the middle, right? So off of tap or whatever, and I drop it in Wireshark, can I read what's in the Graphiant label natively after I handle all the encryption I have to do in the middle and all that?
Yes.
Okay. So it's end to end. Obviously, I'd have to figure out how to get around all of that. But if I did look at it, is the label like usable in some way to me, or can I not really make any sense of it? If I'm
You can read the label, but it's probably going to sound like
it's
gibberish.
just like a string. But
Just a bunch of bits.
thanks. Just curious how it looked on the
Yeah, absolutely.
wire.
So the last part is the IPsec header. That one is just the integrity protection. So this is the traffic that's going over the internet. So we want to make sure any traffic coming from the edge, going to the core, it's integrity protected. which brings us to what happens within the core. So you can see that once it's reached the ingress core, we can strip off the IPsec header. We know we've integrity verified that packet, and now it's going to be switched through the core using the Graphiant label.
But the ESP header is still intact, which
Yeah.
is
The end.
how you're providing the end-to-end encryption.
Exactly.
Right? Okay.
And now, when it's at the egress core, trying to connect to the remote edge, we're again going to put an integrity verification IPsec header to make sure that, again, it's going over the internet. We know that it's a legitimate packet. Once it reaches the edge, it's going to verify the integrity. The IPv6 address is for that receiving edge, so it strips that off. It does the decryption because now this is a packet destined for it, and it returns back to the original packet, and it simply forwards it over to the final destination, which would be the application or the host.
And is the IPv6 provisioning of all of the edge nodes, is that done automatically?
Yes.
Okay.
You don't have to worry about anything that happens in the core
Okay.
or edges connecting to the core.
The edge to core IPv6 is strictly for the overlay.
The edge, yes, just for that part of it. Exactly.
So it really doesn't matter even if the ISP supported v6 or not.